Good.
And good. Hi, good evening. I'm Jonathan. I work for Microsoft Research, and tonight's talk is about giving you a little bit of a glimpse at what we do, and specifically about software verification and how we use the methodology of software verification for our cryptographic library. I believe this is a topic of interest. A lot of software projects need a cryptographic library, and it's also a good way to, like, maybe if you've never heard of it, to figure out what's going on with software verification, what's the state of the art when you're trying to show that your programs are bug-free and do the right thing. So Project Everest is a pretty ambitious research effort that brings together not only Microsoft Research, but also Carnegie Mellon, the French Institute for Computer Science, INRIA, and the joint research center between Microsoft Research and INRIA. We have a very large list of collaborators. We're a bunch of fun people. We can smile in pictures, and some of us live in Building 99. So the initial motivation for that big software verification project was the realization that there's one piece of software that's absolutely critical, and that's the HTTPS ecosystem. HTTPS is of course used to connect to a website with the browser, but it's also used in a lot of other contexts. When you have two machines communicating together in the cloud, they use encrypted traffic. When you do email, when you use voice over IP, VPNs, the protocol that underpins those secure communications, specifically TLS, is pretty much everywhere. And this is an old slide because now way over half of the internet traffic is currently secured with HTTPS. And it turns out that the HTTPS ecosystem is fairly complex. So in addition to what happens is that all these clients use a whole software protocol stack. So you think of HTTPS, but you also have to think of the certificate library, the parsing of certificates known as ASN1. There's the protocol itself, TLS, which basically governs the exchange of messages between the client and the server, where you negotiate parameters, cryptographic keys, nonces, and all sorts of other things in order to establish a connection. And once you've done that, there's also a whole variety of a marvelous collection of different cryptographic primitives that all appear at some point or another in the process of establishing and running a secure connection. And the reason I'm so interested in that research area is that there's pretty much every single bug, every single variety of bug you could possibly think of has been found in the HTTPS ecosystem. And it's the variety is astounding. You have buffer overflows, but you also have incorrect state machines that allow you to transition to the phase that says, let's start talking while the keys are still 0, 0, 0. There's of course parsing problem, because you have to parse certificates coming from the network. So you can have an adversary trying to give you an maliciously crafted certificate. And of course, you may have bugs in the underlying core cryptographic algorithms, either memory safety or functional correctness, or even side channels. And it turns out that pieces of software like OpenSSL have never been secure. They've always been finding bugs every month. And so the whole goal of Project Everest is to set out to say, hey, now we're going to use the methodology of software verification to write that whole software stack from scratch using state-of-the-art research tools, give you the same performance that you had before, but with a theorem that says that the code is doing the right thing and doesn't have any bugs. So we really set out to tackle all of these subcomponents. And Project Everest is a long-run research effort that is set out to span at least 5 years. And one of our goals, one of our explicit goals, is to deliver software that people can use. And in the process of improving our research tool that we use for that purpose. Are there any questions at this stage? I just don't know how familiar everyone is with software verification. So we've been 3 years into that project, and we've had so far a fair amount of impact. We've had a variety of research papers at the bottom, but we also have applied a research methodology to a whole chunk of TLS called the record layer. We have had a deployment of our verified cryptography in Firefox in 2017. We have a library called the Hackmestar library, or verified cryptographic primitive, that's been used in also a variety of software projects. The Wireguard VPN, which is a brand new state-of-the-art VPN, is also using our cryptography. The Quick implementation in Windows, Quick is a new protocol that is setting out to replace TLS, is also currently using bits of our verified software stack. Blockchains are very interested, so of course they want to use it too. We have also developed a library of parsing combinators to try to tackle that thorny problem of property parsing stuff that comes in from the network. There's a unique kernel called MirageOS that's also using our stuff. And Azure, and in particular the Confidential Consortium framework, which is an enterprise blockchain, as I understand it, is also using some of our cryptographic code for their software. And so we, of course, hope to do much more and many more things in the upcoming years. What I want to tell you about is I cannot introduce the entire software stack in the span of 45 minutes. It's a huge piece of software. So the way that I present it at a high level is the top of the pyramid is the protocol. It's the part that handles the state machine when negotiating with the server. That says, hey, I want to negotiate these protocol parameters, that suite of algorithms, I'm going to use these parameters to do so. And you do a back and forth with many messages between you and the server. For that, you have to show things about the state machine, that the state machine is never sent into the weeds, that you have confidentiality and integrity, and in a sense, that's the top of the pyramid. We're still actively working on that top part. But that protocol, TLS, that handles your secure connections, also need like some sub-components, some core building blocks that it turns out have had a usefulness of their own. So for instance, we developed a set of verified parser combinators that allow you to parse binary formats, which we apply to the TLS network format, but also have a usefulness beyond just TLS. So that is EverCrypt, and we're kind of phrasing it and facing it as some piece of software that's useful beyond just TLS. And even though there's a lot to say about protocols in the top part of the pyramid, and there's a lot to say about parsers, what I want to focus on tonight is our collection of cryptographic algorithms that is used all throughout TLS. And the reason I want to focus on it is that there's a nice interaction between the code that we deliver, between C and assembly as we deliver it into existing software, and also because a cryptographic library is a pretty commonly used piece of software. Yes?
What do you mean by functional correctness?
So I have a couple slides coming up.
Okay.
Can I?
Yeah.
Okay. So what I call a cryptographic provider is a library that brings together an exhaustive suite of algorithms. Think of it as SHA, you may have heard of it, RSA, PSS, Polygon 305, Cha-Cha-20, AES. All of these are individual algorithms, and a cryptographic provider usually bundles them all together into a unified library. You always have multiple implementations of each algorithm because you want to get maximum speed. And so it's important that you have implementations tailored to the capabilities that your CPU supports. Oftentimes, these algorithms are grouped under a coherent set of APIs. For instance, all hashes should be usable through a single API so that you don't have to rewrite the code if you want to upgrade from SHA-2 to SHA-3. And the library should be capable of picking automatically the best implementation for your CPU. And so a cryptographic library is really an essential piece of software that may be used in file encryption, secure enclaves, document signatures, cryptocurrencies, basically any modern piece of software. And I'm sure you know many existing cryptographic libraries. Ipsodium is one of them. OpenSSL is another one of them. There's Embed for embedded systems from ARM that has one built in, and the one from Microsoft is called bcrypt or Windows Cryptographic Library. So what we're offering is another verified library that wants to compete with those with the extra guarantee that it's verified. So I want to illustrate what it means to really verify an algorithm, what it means really to have functional correctness with a little example that hopefully will give you a flavor of the challenge. So that's a throwback, and that's a picture of younger me when I was still doing math in my undergrad. And when I was doing that math that I've since forgotten, but I rediscovered that recently, there's finite structures, there's finite fields, and one way to define a finite field is to take a polynomial ring. So if you want to define the finite field Q, when Q is of the form P to the nth, when P is a prime number, you can just take the ring of polynomials where the coefficients are in GFP, and then you quotient that ring by an ideal, and you get a field, and that's the theory. Well, that's the math. I'm willing to trust the math, but it turns out that if you define that structure, it has a lot of very interesting properties that allow you to do actual cryptography with it. So, for instance, you because you're equipped now with an addition and a very fancy multiplication, you can define polynomial evaluation. And if you can evaluate polynomials in that field, then that gives you what's called an authentication code, basically something that's very hard to invert and that will guarantee that your message is authenticated. So from that fancy math data structure, we're getting like a very important idea, which is that we can authenticate messages with that. And that's actually the foundation of AES-GCM, for the authentication part of AES-GCM, with a very specific instantiation of the general pattern. So that would be the application of the math. And so once you've said, hey, here's cool math and I can do something useful in cryptography with it, now comes the time to describe how you're actually going to do it. And so now you can look at the PDF of the first person who presented that data structure, who started detailing it and saying, all right, here's some pseudocode to do it. Here's another more optimized pseudocode that tells you how to do it. You can also pre-compute tables because you can even go faster with that. And here's how you're going to implement it in hardware. So that would be the algorithm. But what you actually want to write in the end is assembly code that goes as fast as you can, that squeezes every leftover cycle from your CPU, where you have comments that say size optimization, size optimization. And that's the reality of cryptographic algorithms. And the challenge of software verification is showing, and that's what I call functional correctness, that this code, this assembly code, that's borderline readable, is actually computing the right math. So at this stage, sometimes there's a reaction in the audience that says, well, I've been writing assembly for my entire career. Like, what could possibly go wrong? So, of course, the reason I'm here is because I have a nice collection of slides with like a nice variety of implementation bugs. So this is a bounce check error in an existing elliptic curve. You also have incorrect computations. You have various bug reports. And so this one says, for the version of 32-bit, you get wrong results, but also there's another code path for SSE2 and AVX. So apparently these are affected too. And of course, the algorithm that I was using as an example also had a bug. And the most recent one was in the Windows cryptographic library. So even professional grade software is not immune to these bugs. You find them everywhere, and it's virtually beyond like the capabilities of even the most gifted programmers to think about all the possible cases and guarantee that their code is right all of the time, always for all of the inputs. So that's where program verification comes in. What we want to state is that if you take this assembly code, this faithfully implements the pseudocode description that was in the algorithm, which in turn faithfully implements the math that was the foundation of the algorithm. So let me give you a little bit of a flavor of what the code we write looks like. So we start from the mathematical proof, the finite field data structure, and we use a special language called F-star, which is developed between several institutions, but chiefly in Building 99 at Microsoft. And F-star allows you to describe the math. So this is a very math-y description of the finite field that describes the specific polynomial that's being used to define that finite field by saying that it has coefficients 0, 1, 2, 7, and the coefficient 1 to the 28. It defines addition and multiplication to just be modulo, and that's it. You've defined in just a few lines the nature of the mathematical field. And that is what you audit. You look at it real hard, you convince yourself with experts that this is the accurate description of the math, and you can even test it on reference input vectors using a big num library. This is horribly inefficient. It's not meant to execute for real, but if you want a sanity check that you faithfully described the mathematical data structure, that's a good way to do it. The next step is to flesh out that pseudocode, the one that I talked about earlier, that's more like an algorithmic description. This is still F-star, we use the same language all throughout, but this is a much more concrete pseudocode description. This one uses machine words to represent elements of the field, where 0 indicates that coefficient 0 and 1 indicates that the coefficient is 1. And then the multiplication is described in an iterative manner with a repeat and bit shifts and ORs and all sorts of machine word operations. So this is still very slow, doesn't talk about any implementation details about how your arrays are going to be laid out in memory or anything of the sort. Think of it as just a functional implementation that describes more precisely how you're actually going to compute the math. And now, if you want to write an actual implementation, there's two technologies that we use for our cryptographic provider. The first one is a tool called Vale, which you can think of as assembly on steroids. That's a dedicated front-end syntax for that F-star language. So Vale allows you to write a very low-level assembly implementation of your algorithm, and you will have preconditions and postconditions. The precondition will say, well, maybe I need that specific CPU feature called pickle mo qdq. Maybe I'm going to have other preconditions to compute that field multiplication, such as the degree must be less than 127. And then the postcondition will be, well, what you find in your registers afterwards in A, B, and CD is the result of actually performing the multiplication.
That's written by hand, that's not refined from the...
This is written by hand. This is where the insight of the programmer comes in, and the programmer must perform a proof that this low-level assembly implementation faithfully refines the algorithmic description that I showed earlier.
So you really know the F-star, code, assembly.
Yes. And then it's a series of proofs you show, and the programmer has to do it with the aid of an automated solver, in this case D3. The programmer has to show that the assembly matches the algorithmic pseudocode, and then we also show using F-star that the algorithmic pseudocode matches the math. So in a sense, you can compose these theorems and get the result that this is faithfully implementing the field operations.
What's the name of that solver?
The Z3. Yes.
Why not use the compiler to compile the pseudocode into the assembler?
So the assembly has been hand-tuned by very motivated people who apparently think it's a really cool hobby to measure and do 12 different CPU assembly implementations on every CPU architecture that exists out there in the wild, and manually reschedule instructions and squeeze the last bit of performance out. So in a sense, this is something that you would not get from a regular compiler, also because these are using very exotic instructions that have been designed exactly for these algorithms. And at this stage, you really want to control each assembly instruction by hand. Does that answer your question?
Not completely, but yeah, I'd be curious of...
It answers the question, it doesn't prove the point. I tend to doubt that a programmer is smarter than a compiler that can do 100,000 different optimizations and compute every possibility, count every key state, so better than a person can.
I should probably say that this is just for the core loops, right? So the really, really hot spots. For the rest, we have another technology. We don't write the entire stack in assembly. This is just for the core loops of the cryptographic algorithms. And in a sense, it's not for us to decide. We don't invent new implementation. We just go in OpenSSL and say, well, these guys have come up with this optimized assembly implementation. They're distributing it on a variety of compiler versions and across different tool chains. They believe that this is the fastest one. Unless someone proves them wrong, we're just going to go ahead and implement that. We leave that debate up to other people who find it an interesting thing to massage assembly code by hand.
Because there's another thing you can do, are you familiar with the bswap instruction? It takes all the bytes in the word it swivels them for little endian and big endian swaps, and people used to always write that in assembler code because the compiler would never generate it. And then somebody figured out that this code they would write in high-level language, the compiler could actually recognize that as a pattern and substitute the bswap in it, even though it doesn't look like you can express the bswap in the high-level language. And that way, the compiler just has to get it right once, and then it's right every time you use it, as opposed to having to revet the assembly language every time.
Yeah,
I mean, that's another way of doing it.
The debate is still up for grabs. I mean, we'd love to use not assembly code if the compilers were big enough, but we're really leaving that debate to Mr. Andy Polyakov from OpenSSL, who will put very opinionated comments in the assembly code saying, on Haswell I get 1.5 extra cycle per byte or whatever.
Okay.
Yes.
Going back a second, what was the significance of writing it in F# to begin with?
So this is just front-end syntax for F-star. Like this is just special dedicated syntax that eventually ends up in F-star.
Okay.
So we can like prove everything in a single language and with a single theorem rather than connecting different languages and semantics.
Okay.
Like, or is your question, why didn't you write it in assembly in the first place?
I guess, yeah, like,
You just need a way to represent the assembly in F-star and to be able to talk about the semantics of assembly instructions.
Right.
And when you've done that, you've basically like come up with a way to describe assembly in F-star for the purposes of reasoning about a piece of assembly code and its semantics. And that pretty much ends up being
So
yeah.
starts with one that used to
So that's the first piece of technology that we use for assembly code. And of course, we don't write everything in assembly because that would be way too much hassle. So for all the rest, like everything that's not a core or hot group, what we use is a subset of F-star called low-star. Any F-star program that's written in the low-star subset is eligible for compilation to C. And the reason we chose C is mostly because, once again, crypto people are very opinionated. All of their code bases are in C. And so if we give them C code out of our toolchain, then they will be much more willing to integrate it. So this is still F-star code. This is a much more low-level implementation of the algorithm. This one has pre and post conditions that say, I require that my input pointer points to something that's live. I require that the other thing is live, and now I'm going to reason about the effect of running that code on the memory, and I'm going to ensure that the only thing that I modify when I call this function is the context CTX. And this talks about operations. It talks about taking pointers into arrays. This is all a bunch of syntax that may be foreign, but what this code is doing is that it's basically doing pointer arithmetic, and all the while, programmer has to verify that you have spatial safety, that you're always accessing objects within bounds, and that you have temporal safety, that you're never doing a double free, or that you're always accessing objects that are still allocated in memory. And on top of that, you have functional correctness, which is basically stating that you are computing the right result. And this is compiled, so Vale code is compiled to assembly, which is just a matter of printing it, because it was written in assembly in the first place. And this one has a dedicated compiler from F-star to C that takes this code and gives you 2 for loops with a bunch of bitwise operations that were being described by a piece of code that was there previously. So that's what comes out of our verification toolchain. C code, assembly code, and the EverCrypt library is about reconciling them together into a comprehensive artifact that developers can use.
sending your code to the Kremlin in the middle of this operation seems like not a good way to sell it.
So it's a pun because it's KNR, as in like CKNR means ML, because F-star descends from the ML family of languages. Yeah, it's a pun, but it used to be funny a few years ago, not so much anymore. Sorry. So just to like recap and really like be super clear about what we verify. So safety. Safety is about making sure that you don't have undefined behavior, that you don't have like out of bounds access, that you don't have dangling pointers. So yes.
Are you including overflows as undefined behavior?
So
Like
only
integer
for signed integer types.
Okay, so
So we don't allow the programmer to reason about it.
you actually have a check for signed
Yes.
integer overflow?
Yeah,
Okay.
the addition on signed integers demands that the programmer show that it will not overflow. And for unsigned integer types, we have a post condition that says that the result is modulo 2 to the 32 if you're lucky with a u in 32. So that's exactly what our methodology is about, like catching all the things that are not legal and showing with a theorem that the programmer is not allowed to write anything of the sort. So for instance, if you want to do pointer arithmetic, there's a corner of the C standard that says that the C compiler is allowed to deduce that a pointer is still live if you perform pointer arithmetic on it. That was like a very known bug in the Linux kernel when they first did pointer arithmetic before checking that the pointer was null. And the C compiler eliminated the null check on the basis that the standard says that you're only allowed to do pointer arithmetic on live pointers, therefore the pointer must have been live, therefore the null check is not needed. Like, it was a super big moment of reckoning for the Linux kernel because they realized that the compiler was doing something unrelated. We say that if you want to perform pointer arithmetic, you have to show with the aid of the theorem prover that the pointer is live before you do it. And of course, there's an auditing phase for that, right? You have to check how we modeled all these C concepts, take the standard on the side, and convince yourself that we're faithfully and accurately modeling that stuff. So of course it's error prone. Like, we found at some point that we were exposing a blit operation, that's a memcopy, and we were not checking that the pointers were not null. And the C compiler is allowed to deduce that if you pass something to memcopy, it must be non-null. Therefore, because we were previously allowing passing null to memcopy, then we could deduce a contradiction and shatter the whole safety theorem. It hasn't been used in a while, but it was a hole of soundness in our model. So we fixed that and changed the precondition of our version of memcopy to demand that none of these arguments are null. And if the programmer may receive a null pointer as an input, that forces them to do an if to check whether any of them is null. Yes?
So you were talking earlier about how you guys are doing these mathematical proofs on the pseudocode and maybe on the assembly as well,
Yes.
with the help of some tools that help you do the proofs. How do you know that the tools don't have bugs that are ruining your proofs?
That is an excellent question. We don't. So the tools themselves that we use are not themselves verified. So the Z3
Yeah, because otherwise you can't. There's like an infinite chain of.
Of course, so it's, yeah, because then you have, okay, so that's the question of the TCB, the Trusted Computing Base, which parts of our ecosystem are we assuming are done right? So there's our language, the backing theorem prover called C3 that tries to perform as many of these proofs automatically as possible. And of course, there's the C compilers. Generally, what we say is that people can choose to use ComCert, which is a verified C compiler. It comes with a proof of correctness that states that the compiler introduces no bugs when compiling from C to assembly, except that there's a performance hit compared to, say, Clang or GCC. So no one wants to compile from ComCert. But in theory, you could if you wanted to reduce the TCP. In practice, this has not been found to be a problem. There are occasionally issues with our tools, but nothing that led to a wrong proof. So we continually audit them. We have paper formalizations, and some other lines of work have verified tools, but it's a trade-off between their productivity and the mathematical elements of your result. And the trade-off that we do is that we don't expend any cycle strength to verify our tools, but we instead are able to verify a much larger body of code. There's some people at MIT who took the opposite stance. They just verified 3 algorithms, but they have a much stronger security result end-to-end because the tool that they use to compile is itself verified. It's at different points in the design space. But yeah, that would be the question. All right, so functional correctness is showing that you're, in addition to not writing beyond the end of an array, you're also computing the right stuff. And another interesting extra property, each application domain has its own kind of flavor of theorems that you want to prove. For the top of the pyramid is something that says if you have established a channel, then you have confidentiality, no one can read it, and you have integrity, no one can tamper with your data. For parsers, you want to show things about how parsers are non-malleable. And for cryptography, one property of interest for that application domain is secrecy. It basically means that you want to avoid side channels. Side channels are when you branch on secret data and your then branch takes longer than your else branch, and an attacker can observe that behavior and deduce whether there was a 1 or a 0 in your private key. So we also rolled that out using discipline in our language by saying that secret data cannot be compared or tested for, or cannot be used to access memory. And that way you avoid timing side channels and cache side channels. So of course, there's a limit, as you currently asked for. So our verification toolchain might be buggy, that's what we just covered. Our specifications might be wrong. Like it may be the case that someone was like, okay, I'm going to write the specification of MD5, and suddenly at the end there's one phase where you have to write a little endian and people put big endian in the specification. So you have a wrong specification, that happens. That's why we test our specifications on test vectors to roll that out. And of course, like when we build that whole pyramid, at some point the security of your secure channel is based on stuff like a hash collision is highly improbable, so we're going to assume that hashes can be modeled as that kind of mathematical structure in order to deduce our confidentiality theorem. So with those assumptions that we usually explain or are very open about, that's how we ended up with headlines such as cryptography that can't be hacked. We had a journalist who was interested in our work, but unfortunately we were not able to check the title for that, so we got a lot of flack for that on Reddit and a lot of other internet outlets. So we need to keep hammering that there are limitations to this work, that we are very aware of them, and that we have to remain modest in the face of our results. So Mr. Bruce Schneider fortunately read the article and realized that the article overhyped our release, but that the project was cool. So we were all very happy to read that Bruce Schneider said that this was a cool project. All right. So let me now brush off quickly about what makes the EverCrypt library and what were the challenges in trying to achieve verification at such a large scale. So EverCrypt is basically verifying a bunch of crypto algorithms using both the assembly-like technology and the C-like technology and bringing them under a single umbrella. We want state-of-the-art performance, we want a single verification result, and we want to deeply integrate that to offer something solid for clients. So we already have a bunch of algorithms. Some of them are just in the C flavor, some of them are in the assembly flavor, relying on dedicated microcode instructions for specific algorithms, such as AES-NI, which is a core CPU instruction that's solely for the purpose of implementing the AES algorithm. One of the core ideas in EverCrypt is that for one algorithm you may have several implementations. And what we show and verify is that no matter which implementation you pick, whether it's the SSE2, the AVX2, or the default one, you still get the same result that's computed. So that means that from the client's perspective, they don't need to know about all these details. All that they care about is that an algorithm is chosen that computes the right thing. And that's why functional specification is so important. What the C code looks like, it's a mixture of runtime checks on CPU features, say for AVX2 and AVX, and a mixture of if-defs that make sure that you're on the right target platform, because otherwise you just couldn't link the program. Another core key concept is that we want to have agility. Agility is the fact that you have many algorithms that essentially do the same thing, and you don't want a different header file for each one of those algorithms. So, for instance, all of the hashing algorithms perform the same stuff. You give them data, and eventually when you're done, you say I'm done, and you get a hash for your data. So we have one single API for that, where only the initial choice of algorithm matters, and that's really important. First, some hash algorithms get broken, so you need to upgrade easily, and you want to change just one parameter, possibly at runtime, rather than recompiling your code. And also because from the proof perspective, it shows that all of these algorithms, regardless of which specific flavor you pick, all implement the same cryptographic functionality. So that's a deeper result than just you can switch between algorithms. This states that all of the hash algorithms compute morally the same kind of cryptographic part. So one of the things that we're really happy about is that you can write algorithms in C, you can write algorithms in assembly, but you can also write them in a mixture of C and assembly. You can write all of the outer parts in C, and the core type group that really matters, you write it in assembly to make sure that it uses the right instructions. And with that, we are actually beating the competition by a sliver of a hair on one specific machine. These things fluctuate, but what it basically means, and that's the real message here, is that verified code is now competitive with state-of-the-art unverified handwritten code. And that's really the message that we want to hammer, that you no longer have to choose between code you can trust and code that is fast. Another aspect of the library is that you can build other things on top of it. You can use a client that's unverified. You can have a C client that uses your library, and the client still gets the benefits of using verified code. It basically means that if there's a bug in that C client, well, the bug won't be in our stuff because our stuff is verified. And we can also build other applications on top of it. One of them is Purple Trees, which is a data structure used for blockchains. And another one is the Signal protocol, which we also have built, which powers communications on WhatsApp, Facebook Messenger, private communications on Skype, and the Signal app itself. So that's the kind of verified software that a solid cryptographic library enables. In terms of efforts, we have written a total of over 100,000 lines of verified code that boil down to 80,000 lines of assembly and 20,000 lines of C code. No, sorry, 20,000 lines of assembly and 20,000 lines of C code roughly. So we're at a ratio of 2 to 3 in terms of like, how much bigger verified code is because of all the proofs, annotations, and things. Yes.
In writing this code, have you been startled at the kinds of bugs that it finds in the code?
We have, like, a PhD student in Paris found a bug in a piece of code that was taken from OpenSSL.
Okay, but I'm startled because it would be the kind of bug that nobody would expect would be in there, and your verifier discovered it.
It was, okay, we've seen, I think we've seen both. We've seen both, like, really bad stuff, like, oh, that code path allows you to read an uninitialized piece of data. Or you did some modular computation, you know, you're unrolling your loop, you are pipelining your stuff manually, and then you need to, like, unwind. So you do that modulo to do less good things, and someone got the modulo wrong when, you know, the modulo is 0 or something. That's that someone should have been much more thorough on paper. We also found, like, really subtle stuff. Like, well, you thought that this assembly algorithm would behave this way, but actually this instruction resets the carry propagation flag of the CPU, and the next instruction was assuming that the carry flag was still there, so now you're missing the carry, and this is only going to happen with an like, infinitely small probability, meaning that there was no way you would have found it with testing. So that was more in the subtle category.
Okay, cool.
And any other questions? And of course, that's a big effort, but you know, we try to keep everything under CI and all work together. This is just a slide to tell you that this is also a leap in terms of verified code. This is a timeline of state-of-the-art verified code in terms of performance. And with that work, where we combine C and assembly, we are able to match the fastest OpenSSL assembly code out there. So it's not like we were slowly creeping towards that limit. There was like a substantial limit. Verification also allows us to verify complicated math steps, like this one. I will spare you the details. It's pretty low level, but the bottom line is, if you want to do some pre-computations or things that rely on deep properties, then you can now check that your math that you did on the back of an envelope is correct. I'll wrap up with a quick word about like who's been using our code and what their experience has been. So I would say the level 1 of using our code is what the people from Wireguard have been doing. The guy who does the VPN software called Wireguard is very research-minded. He's been verifying his protocol with state-of-the-art research tools, and for the cryptography that his VPN is using, he's trying to do it right and land the Linux kernel a brand new cryptographic API. And as I was preparing this talk, I found that gem on the Linux kernel mailing list where some guy is just saying, yeah, well, this one is known to fail because it uses caribits, and well, that one is definitely broken, and that one might be too. I'm working on a patch. So the Linux kernel has broken cryptography in there, and they know it, and they seem to comment about it like it's the most thankful thing in the world. So that guy who's like writing the VPN software that needs kernel modules also has said, okay, I'm going to like land some decent cryptography in there. So what he does is he just combines multiple research projects together. He uses some of our code, he uses other code coming from MIT, and they don't take the algorithms they don't want and then rely on the kernel level CPU detection stuff. So it's kind of a cherry-pick approach. Firefox also does that. They have their NSS cryptographic library, and they just pick the algorithms that they want. second approach is you just take the whole library. You have the thing wholesale. And there's some areas where it's really important. IoT has had a lot of bad security failures. Blockchains are really terrified that they're going to have a breach of security somewhere and someone is going to run away with millions. So there's some sort of like very good peer pressure in the blockchain community where everyone is like trying to one-up each other with the safest cryptographic code. And for that, they're really very much willing to use verified software. Third, like the next level of collaboration is, I would say, you have an algorithm, and we have a group who's like that at MSR. They're working in the post-quantum world, and they're designing post-quantum algorithms, and they're competing in the NIST competition for determining what will be the official next post-quantum algorithm. And for that, because these algorithms have had so many failures, what they're doing is they're also trying to verify their code ahead of time in the hope that it strengthens their submission for NIST. So that's the different kind of integrations that we have. And the other way to see EverCrypt out there in the wild is as a building block for other verified software. So one example is Quick Crypto. Quick is that brand new IETF protocol that fuses TLS and TCP together in order to reduce latency and achieve stronger pipelining on the web. It's shiny, it's fresh out of the box, it was initially developed at Google, it's being standardized, and of course it uses a lot of fancy cryptography. So if you want to implement Quick, you need a toolbox of cryptographic actions for packet number encryption or whatever other feature of Quick exists. And with EverCrypt, we're able to have a strong foundation for verifying that toolkit of cryptographic actions needed for implementing the Quick protocol. And some of that is being used in Windows. And of course, you get memory safety, functional correctness, and you also get a strong proof that says that assuming some of the cryptographic primitives are not broken, then you get a strong cryptographic result. Another component that was built atop EverCrypt is a Merkle tree library, which is a data structure that allows you to authenticate a large number of transactions and is used in the blockchain. And what is very cool with that data structure is that we have a proof on top of everything else that says if the security of your Merkle tree is broken, if you have a collision in your Merkle tree, then it must be the case that the underlying hash function is broken. So that's a security reduction proof. It means that any failure in your library can be traced down to a failure in the underlying or cryptographic primitive. And for that, well, it's another job. It's being a cryptographer. Right now, cryptographers believe that the SHA-2 family of functions is still strong enough. They know that MD5 and SHA-1 are broken, but at least you know that you didn't screw up in the Merkle tree, because any failure can be traced down to a cryptographic failure. So your data structure is as strong as it can be. That one is used in the confidential consortium framework. And the last application that I briefly mentioned is Signal. That's being used by WhatsApp, Facebook Messenger, Skype, etc. It's a very sophisticated protocol, and there's a lot of guarantees that you get. And we use the algorithms from EverCrypt to implement the actions of the Signal protocol, such as triple defilement or double ratchet. One new pipeline that we have is, in addition to the C toolchain that gives you C, is we have extended the compiler that compiles F-star to C with a WebAssembly backend that is very small, that just fits into a couple thousand lines of ML, that has a very straightforward compilation scheme, but at least it's auditable, and you don't have to trust all LLVM to compile to WebAssembly. So we have compiled our cryptographic primitives, and we see that as a real opportunity because the situation of cryptography on the web is really sad. You either use the Web Crypto API, which really lags behind in terms of support for modern cryptographic algorithms, or you have to compile your cryptographic library to WASM using Emscripten, and that's a lot of code to trust. And we have found some issues, like bad issues, set channels that were being introduced by Emscripten when compiling. So that is what we've been using as our new application domain. We're really trying to push EverCrypt also as an alternative if you want to write web applications. And if you have a custom scheme, or if you have things that are not yet supported by the web platform, then maybe you can integrate EverCrypt in your web context. And the thing to remember is that web is not just web pages, right? A lot of desktop applications these days are written using web technologies. Skype, Signal, the VS Code editor, all of these are just Chrome, the browser repackaged without the user interface of Chrome as a desktop application. So the web is really an important use case for us. So to wrap up, the message that I want to state is if you have a large software development and you need a cryptographic library and you're in a very security sensitive domain, then this might be an option for you. Our bindings are in C, but that's okay. If you're to call them from C++, we can extend the API with a handwritten thin layer that just has RAII or something. Some application domains have some sort of very good peer pressure, like blockchains, where they're really trying to get it right from the start. And that's also because they're starting from scratch. The field is relatively new. They don't have the legacy of the past. And they're also like open source. So like, we've seen historically open source projects adopt their stuff much more easily because they seem to be more nimble. What I would like to see in a few years' time is that if you're using a legacy crypto library that is not verified, then this might be a liability. And I would like to see guidelines in a few years that say, hey, verified software is not applicable everywhere, but for a select few critical components, it's ready. You can use it and bring it into your codebase. That's it. Thank you. Yes.
Some of your very first slides, you were showing everything under HTTP2. What about a direct secure socket directly running to the TLS? I'd like to just have it here. You create your connection in a couple sockets, you pass it off to your TLS connection library, and just use a socket type API for reading and writing where it does all the crunching of the bits and shoving it out of the wire itself. Where you can basically just do direct C API to the sockets as opposed to having to run through a web interface.
So that's like the top of the pyramid. We're still working on that. We haven't finished the verification of that. That's what you will get in the end. Like when the TLS library is complete, you will get a socket-like API where you can establish a connection between two endpoints.
Without all the baggage of the HTTP2.
It's just one component of the HTTPS ecosystem, right? So you can always use the TLS library standalone as just something that allows you to send and receive.
Okay.
You might build more stuff on top of it, but the core idea that you can establish a secure channel is not specific to the web. Yes?
Going back to the point on functional correctness, and I apologize if I'm coming to this conversation with not a strong enough background. So I can accept, without a full understanding, I can accept that F# is a domain-specific language that allows you to make certain assumptions and perhaps can verify that the mathematical proof aligns with the code as it's written. How do you carry that proof and that confidence forward when you translate it into assembly? Is it a series of tests or assertions?
It's still mathematical verification, so it's still as strong as a theorem, and it still states that it works right all the time. So let me give you the example of C of how we go like down about here. So for C, okay, so you buy going from concise mathematical description to pseudocode.
Sure.
Okay, so you have to write loop invariants. You have to say that this series of bits can be connected to a field element, and you will write all sorts of lemmas, additional side theorems, and all sorts of proof steps that will allow you to connect the pseudocode to the mathematical description. So you can say, for instance, it's as if...
Taking into account the real-world constraints of things like signedness.
Okay, so
that
let's
doesn't
go
apply
down to real world.
Right.
So what we do then is we model in F* low-level concepts. So we have models for machine integers with preconditions that say you can't overflow signed integers, or preconditions that say you cannot divide by 0, and all of these are like obligations that the programmer has to satisfy and demonstrate every time they want to use those libraries. So you've moved from the world of mathematical integers, which where you were when you were doing math, into a world where your only instruction is fixed with machine integers. You can still connect machine integers to mathematical integers. You can say the value of a runtime low-level machine integer can be seen at the proof level as just a mathematical integer with the understanding that it's between 0 and 2 to the 32nd minus 1. Okay, so now you've connected a low-level concept with a proof-level concept. And you can say, okay, imagine that you just do your textbook multiplication algorithm, where you just repeatedly multiply. Then, because your machine integers are 4-word bigs, so you're just going to do, like you're going to allocate an array of 8 words, and you're going to use that temporary to perform the textbook multiplication, computing all the intermediary results, storing them, determining whether there's a carrier propagation to be made, and then computing the result. We're going to say the proof that all of these operations compute the right mathematical operation. And you're going to have to prove things and to show intermediary theorems. Like, okay, if I do the second row of my textbook multiplication, that corresponds to that mathematical integer, which in turn, when summed with all the other ones, will produce the intended result for the multiplication. So you connect the row-level concepts to the proof-level concepts, and every step of the way, you have that F-star language that's nagging you and telling you, I don't understand why this is true, I don't understand why you're computing the right result. Please provide more explanations as to why this is right. And we do the same for memory. We model memory as a set of restrictions on how you can operate. We model the stack. We say there exists a series of stack frames. When you allocate something, it lives in the topmost stack frame. If the topmost stack frame is gone, your thing is no longer live and you're no longer allowed to use it. And we model all of these, like we build a tower of concepts that allow you to put yourself in that low-level setting where everything corresponds to the restrictions that you have in your programming C. And your job as like a proof person is to connect a series of low-level operations to the mathematical specification.
And in what way does F-sharp actually nag you when you're outside those constraints?
Oh, it just says I couldn't show that that is correct. And it just rejects the program.
Is it using some sort of SDL or something that you're wrapping around the code that says like this chunk of code corresponds to this assertion that I've made?
So each piece of code is transformed into a logical formula that faithfully describes the meaning of the code. The logical formula is combined with what you know as a precondition and what you're supposed to show as a postcondition, and then you reduce the correctness of the program to the satisfiability of the logical formula. So we encode your program as a big logic formula, and if you can show that the logic formula is true, then your program is computing the right thing. So we send that big logic formula to an automated solver called C3, whose job is to try to find proofs automatically. But it's not a decidable problem. So unless you provide enough lemmas and intermediary steps of reasoning, the solver is not going to figure it out on its own. So you litter your code with assertions or calls to auxiliary lemmas or pieces of reasoning that guide the solver to the conclusion.
Okay. Does that mean that if somebody went in and made a typo outside of like those lemmas and assertions, that the server can catch it, or is it up to an actual reader to identify that the assembly on the page doesn't match these assertions?
It's a type checker, so it will find it for you.
Okay.
If you put a plus instead of a minus, the logical formula would be false, and you will get an error saying, I'm not accepting this definition because the proof is not going through. So if F-star says yes, it means that your code is correct, and you may proceed with compiling. Proceed or asking.
Okay. Thank you.
So what do you think of efforts like security evaluated L4?
I see L4?
Yeah.
It's the same space as us, right? Yeah.
They use Haskell versus, they just use Haskell versus F-star.
Do they compile to C? Like, do they give you low-level C code?
Yeah, I think they this tool called Haskell that takes the Haskell. So it's a similar approach.
Yeah, they just chose to do an OS. We're focusing on the cryptographic library. Like, these would be the people that go to the same conferences that I do.
Because you think this approach you could correspondingly do on microkernels or other reactive systems?
It's a research challenge. I don't know how well that can scale. One of the important things is that we're not modeling every crazy thing from C. Right? In C, you can always do stuff like observe whether two objects are allocated next to each other, and then there's a raging debate about pointer provenance as interpreted for the canon, about whether this is legit. Like, we're not modeling crazy stuff.
Do you think it would help if you refine to a more modern language like Rust, which had better defined semantics?
It's a trust problem. Like, of course, we would love to go directly to LLVM the reality is, if we want to be taken seriously, people want to see the C code.
Okay, so it's a really cultural problem in the
Yes.
industry today. We're love for
Absolutely.
CECO.
Yeah.
It's not scientific.
And the Kremlin compiler does a lot of work to eliminate a lot of verification artifacts. Like, for instance, in the process of proving things, you may do super modular code because it's easier to prove properties about small functions. Suddenly you have that beautiful tower of abstractions. No one wants to see that in their C code. The compiler will recombine functions for you. You have 10 different files that correspond to some big logic about what it means to model big non-integers. And they're all compressed into one C file because no one wants to see that. A lot of intermediary variables are removed. Like, there's a lot of work involved in generating really neat C code.
So you worry about psychological complex and other things where human beings who have to see the code want to make C code that's palatable.
It's like, and they did read it. Like Mozilla, when we first started engaging with them, we gave them a elliptic curve, and they read the code. And they saw artifacts of the code gen, like an if with an empty then branch. And they were like, not acceptable. And I was like, it's generated code, what are you guys doing? So there was a big phase of reckoning. Like, another anecdote.
Your code actually looks better than OpenSSL, so yeah.
Oh, it's not very hard, is it?
It's not so hard.
So, but another anecdote that I often recall. So when I wrote the pretty printer for the C code, so the very end of the pipeline, I had a description of like an AST with operators. And so I took the standard and looked at the operator precedence table and wrote a printer that would insert parentheses only when needed. And of course, people came back screaming at me saying that they were getting all sorts of compiler warnings because apparently no one can remember the precedence of left shift and bitwise or initially I was very gung-ho, like this is auto-generated code, you shouldn't be looking at this, and then of course, like 1 week after I wrote the 3D printer, I had forgotten myself, so then I became much more amenable to the idea of adding more parentheses than was strictly necessary. So there's a lot of that, like small things that make a big difference if you want to be taken seriously. But you're absolutely right, it's totally a social problem.
Yeah. Is EverCrypt currently certified? Have any kind of certifications, or are there any plans for doing such a thing? For
No.
example, no.
FIPS?
Yeah.
No.
No.
To network it. The way we look at FIPS is it's for a very specific use case, like government agencies that have like really weird requirements, and for us, I don't think we have the same goals. And also, if we change the code, we lose the FIPS certification. And that's like if we had crazy resources, like if Microsoft was like, this is a flagship project, we're going to give you, a lot of people, and then we can allocate people to FIPS certification. And sure, why not? But right now, we're mostly trying to convince people that it's a viable approach, and that we should get more manpower and commitment behind this project because we believe that a verified cryptographic library is useful to the world and software ecosystem at large. FIPS would be a plus. What would be even better is if FIPS certification people understood formal verification and could vouch for the seriousness and the strength of a library based on the fact that it's using formal methods. So the airline industry went through a similar phase. If you're familiar with the O178C, it's the, I think, European agency that certifies airplane flying control software. And they had enormous norms that were mandating like millions and millions of tests that were taking up to 3 months to execute. And Airbus was really unhappy with having to certify all of their control systems with these stringent requirements. Airbus is in the process of trying to switch to a verified C compiler. So it comes with a theorem that says any behavior of the compiled code was allowed for the C standard. And so with that, they also are influencing the certification agency so that they lift a lot of the testing requirements that were initially for the purpose of checking that your code was not misleading. So I would love for the cryptographic certification industries to have a similar progression where we get a shot at telling them about formal methods and they're like, oh, so that changes the game and maybe we don't need to be so stringent and have such a extensive certification process if you're using state-of-the-art verification.
Okay,